Hello everyone, welcome back to Spectrum classes. In this video, we are going to perform a lab activity and the aim is determination of distribution coefficient Kd for iodine in water and n-hexane system. So here I am just going to elaborate what is called partition coefficient. So before that, in which apparatus we are going to perform this experiment. So here I am going to show you this pear-shaped flask, and this is called separating funnel. It is of pear shaped. So here we are just going to show the chemicals which are going to use here. We are going to show you the chemicals which are going to use here. So we are having the saturated solution of iodine and two different layers of solvents. One is n-hexane, this dark brown color, which is shown over here is n-hexane, which is 20 ml, and here it is water, which is 100 ml. So we have taken this in the separating funnel to separate out after the equilibrium established between these two layers. Now coming to the equilibrium part. So here I am just going to show you that with this simple setup. So here is a beaker, and in this beaker iodine, which is our solute, and this iodine is partially soluble or very less soluble in water, but it is highly soluble in organic layers. So here we are using organic layer as n-hexane and the aqueous layer water, distilled water. In this, if we are going to dissolve iodine, so for that purpose we are forming saturated solution of iodine in n-hexane. And when these two liquids come in contact, this iodine which dissolved in the organic layer, it distributes itself in organic as well as in aqueous layer. So here an equilibrium is established. Once the equilibrium is established, for that we are just going to calculate the equilibrium constant of iodine between two different immiscible layers. That is the condition. So these two are immiscible, and in this the solute distributes itself. Once the equilibrium established, we are going to calculate the equilibrium constant, and this equilibrium constant is known as partition coefficient, and it is represented by Kd, and here is the formula for that Kd, partition coefficient. So the concentration of solute, that is iodine, in phase 1, suppose we are taking phase 1 as organic layer, and it is divided by the concentration of solute in phase 2. So iodine concentration in aqueous water layer. This experiment has several applications, but here in this video I am not going to elaborate. We are going to discuss it separately in the next video. Now the number of steps involved in this lab activity. So first of all, preparation of solution. So this many solutions we required for this experiment. One is saturated solution of iodine in 50 ml of n-hexane. I have prepared in 50 ml. You can prepare it in 100 ml also. M/10 solution of potassium iodide. M/10 solution of sodium thiosulfate. M/100 solution of sodium thiosulfate, and starch solution which is freshly prepared. Now second part is standardization of solutions. So this standardization for this sodium thiosulfate we need to do, because this is not our primary standard. So for this purpose we are going to standardize this sodium thiosulfate against potassium dichromate K2Cr2O7 solution. For that purpose we do require 10% of potassium iodide and M/10 solution of potassium dichromate. That we are not going to discuss here, because I have separately made a video on the standardization of sodium thiosulfate and how to prepare sodium thiosulfate solution. So two different videos I have already made. I will give you the link of those videos in the description box. The third one is titration of iodine versus sodium thiosulfate. So the iodine which distributes itself in the liquid, aqueous and organic layer, we are going to separate out them and then we are going to titrate against this. M by 10 sodium thiosulfate is used to titrate organic layer, and M by 100 solution of sodium thiosulfate is used to titrate aqueous layer, and this starch solution is used as an indicator. And in the last we are going to do the calculation part and we are going to discuss the results. And to prepare this many solutions, these solution M by 10, M by 100, what we need to do? So we are going to follow this formula. So if I want to prepare M by 10 sodium thiosulfate, so you put M by 10, multiply it by molecular weight of sodium thiosulfate and the volume in which you are going to prepare, say 500 ml or 250 ml. To convert it into liters, we need to divide by 1000. So here you will get the weight. So the weight which comes from this equation, you dissolve that in the V volume, whatever you have chosen over here. So this is how you can prepare the solutions. Secondly, once we prepared M by 10 sodium thiosulfate solution, from this we are going to prepare M by 100 solution of sodium thiosulfate. For that purpose, we are going to use M1V1 is equal to M2V2 equation. Here I have written N1V1 is equal to N2V2. Since sodium thiosulfate molar solution is equal to normal solution, therefore I have written over there this equation, normality equation. Fine. Now we are going to start the lab activity. So to prepare saturated iodine solution, we are going to have 2.5 grams of iodine in 50 ml of n-hexane. You can repeat the same experiment in carbon tetrachloride. Since that is not with me, so I couldn't do that. Here we are preparing three sets. One is 20 ml of organic layer, 100 ml of aqueous layer. Here 15 ml of this saturated iodine solution plus 5 ml of n-hexane. Here in the third set 10 ml of saturated iodine solution and 10 ml of n-hexane. So first I am going to add 10 ml of n-hexane to the third set and now 5 ml of n-hexane in the set 2. And now I am going to take 20 ml of saturated iodine solution that I am going to transfer in the set 1. This is the saturated iodine solution 20 ml. Now in the second set we are going to take 15 ml of saturated iodine solution and we already added 5 ml of n-hexane to the reagent water. So here it again forms 20 ml. Now in the third set we are going to add 10 ml of saturated iodine solution, and in this third set we already added 10 ml of n-hexane. So in this manner, in 3 reagent bottles we are having 20 ml of organic layer. Now to this we are going to add 100 ml of distilled water in each reagent bottle. So I have added 100 ml to the first set. Now I am going to add 100 ml to the second set. And now I am going to add 100 ml of distilled water to the third set. So here, after adding this distilled water, we are going to shake the reagent bottles, and since because of organic layer there a pressure becomes, so release this pressure after losing the stopper on the reagent bottle. So here you can see the color in the aqueous layer, and it is clearly seen as the concentration increases, the color increases. So in the first set we are having dark color as compared to second and third. Repeat the same shaking procedure after each 5 minutes, after every 5 minutes for 30 minutes. And once you complete the procedure for 30 minutes, leave it at room temperature for 30 minutes at least, and then separate the organic and aqueous layer. So to separate the organic and aqueous layer, we are transferring the solution from the reagent bottle in the separating funnel. So here you can clearly see the aqueous and the organic layer. So this aqueous layer which is at the bottom, we are going to collect this in the reagent bottle. Once it is reaching to the bottom, we are just going to stop the nozzle, and now this part of aqueous layer we are just going to discard. Here you can see the tip is filled with the organic layer. Now we are going to transfer this organic layer in the another reagent bottle, and the same procedure is applied to all three sets to separate the organic and aqueous layer. Now we are going to prepare the thio solution. So for that purpose we are going to take 12.45 grams in 500 ml, and we are also going to prepare potassium iodide, for which we are going to take 1.67 grams of potassium iodide in 100 ml. And from this thiosulfate solution, which is n by 100 we prepared, we are going to prepare m by 100. So from this m by 10, we are going to prepare m by 100 in 250 ml. For that purpose, I have to take 25 ml of m by 10 solution, and I am going to transfer it into the measuring flask of 250 ml and make up the solution up to the mark or 250 ml. So in this manner, we are going to prepare the solution of m by 100 sodium thiosulfate from m by 100. So in this manner we are having three solutions: m by 100 thiosulfate solution, m by 10 thiosulfate solution, and n by 10 Ki solution. Now preparing the starch solution. So for that purpose I have dissolved 1 gram of starch in the warm water and heated up to 70 degrees centigrade and then cool down to room temperature and filter it. Now we are going to rinse the burette with the m by 100 sodium thiosulfate solution. After rinsing, I am just going to fill it. So fill it up to more than 0 mark. So because we need to fill this nozzle also, bottom part. So here I am going to fill the bottom part, right? Now it is up to 0, and now I am just going to clamp it in the burette stand. So with the help of this m by 100 sodium thiosulfate, we are going to titrate our aqueous layer. So from this aqueous layer I will take 50 ml, and before that I am going to take 10 ml of Ki solution which we prepared. So here I am going to rinse, and now I am going to take 10 ml of potassium iodide solution, m by 10. I will first transfer it into the conical flask. 10 ml of n by 10 Ki solution. So I am going to transfer it into the conical flask. Now I am going to transfer 50 ml of aqueous layer. This is of the third set. So here you can see 50 ml of aqueous layer. You can perform this experiment with the help of your pipettes. Now I close the conical flask with the petri dish so that iodine cannot evaporate out of this, and meanwhile potassium iodide form Ki3 complex. Now we are going to titrate it with the help of m by 100 sodium thiosulfate. Once the color is faint or light yellow, we are going to add the freshly prepared starch solution, 3-4 drops. So here you can see the purple color of the starch iodine complex. Now we are going to titrate it till the colorless solution appears. So near the end point we should be very careful, because each drop contributes towards the error. Here we should be very careful, otherwise error is added. So it is colorless now, and we can measure the burette reading. This is only for the laboratory purpose or record point of view. If you are doing research, then you should be taken extra care for this, and you should use pipettes or then as well as calibrated glasswares. Now the same procedure is repeated for other sets, set number 1 and 2 as well. So here I speeded up and I am performing the same experiment with set 2. Here we are going to have colorless solution. This is the end point. Now we are going to record the readings that we are going to use in the calculation part. So again I am going to add 10 ml of potassium iodide, 50 ml of aqueous layer from set 1. I close it and now I am going to titrate it with m/100 sodium thiosulfate. Once the color is little fainted, we are going to add starch. In this set I have added 2-3 drops extra, which again cause an error, so try to avoid such kind of errors. Now the reading. Now we are just going to transfer this m/100 sodium thiosulfate solution from burette to the measuring flask. And now we are going to rinse our burette with m/100 sodium thiosulfate solution. And after rinsing, we are going to fill it with m/10 sodium thiosulfate solution for titrating the organic layer. So for that purpose, I am taking 10 ml of organic layer with 10 ml of Ki solution. So here I am just going to transfer 10 ml of Ki solution. Now I am going to transfer this organic layer 10 ml, and here you can see the change in color because the iodine which is present in n-hexane, it is forming Ki3 complex in the aqueous layer. And now we are going to titrate it. After properly shaking, so that maximum amount of iodine is extracted in the aqueous potassium iodide solution. So here you can see the color. So from organic layer, it is transferred to the aqueous layer and it forms a complex with potassium iodide. Now we are going to titrate it. Once the color is fainted up to yellow, then we are going to add our starch solution, because at the starting if we added the starch, it forms a stable complex. Now I am going to add this starch and you can see the color change. Now we are going to titrate it, and here the last drop to continue to reach the end point. Here we should be very careful. And in case of organic layer, you can see here you can see n-hexane as well as water. I hope you are able to see this. Fine. In the same manner, we are going to read the readings. So it is about 4.4, and the same procedure is repeated for set number 2 and set number 1. Here I speed just to save the time, and here you can see the color change, and we are now going to titrate it. Here the color is fainted. Now we are going to add starch solution, 2-3 drops. You can see the color of starch iodine, and here you can see the end point is reached. Now we are going to take the readings, and same thing is repeated with the set 1. So 10 ml of potassium iodide and 10 ml of organic layer. And this is a kind of redox titration, iodometric titration. Now again we are going to titrate it, and it is more concentrated as compared to the set 2 and 1, 2 and 3. And now we are going to add starch. Here you can see the color in the organic layer, which is slowly disappearing, right? So you should be very careful at this moment. And now we are going to take the readings and we note down in the answer sheet. So we have seen the lab activity, and here we are going to discuss the chemical reactions involved. So here if we are going to write down the reaction between sodium thiosulfate and iodine, so here we are having this sodium thiosulfate, how it is react with the iodine. So the reaction is given by this. The important point, since it's a redox titration and it's a redox reaction, means gain of electron, loss of electron. So important thing is that we need to calculate the oxidation, change in oxidation state. So sulfur and iodine. Here I have written change in oxidation state of iodine. So here iodine per formula unit, it is changing by 2. It gains 2 electrons, right? Change in oxidation state of sulfur, which is per formula unit, it is equal to 1. So here in this manner we can write down that against 1 mole of iodine, 2 moles of sodium thiosulfate is consumed. Therefore, the calculation part we are using this equation. Now this I have elaborated these two, A1 and A2, and we are just going to put over here. So for the calculation part we are using this formula, and here A1, A2 I have mentioned over there, and we are going to use this equation to calculate the partition coefficient KD. So what we have done, we have taken here, I am just going to write down 50 ml of aqueous layer I have taken, and this 50 ml of iodine is titrated against m by 100 sodium thiosulfate solution, and the volume consumed is 6 ml. These three things we are going to put over here in this equation. So volume is 6 ml, m by 100 sodium thiosulfate solution, and here 50 ml of water is taken, right? So what will be the m value of m1? So m1 is calculated here. I am just going to write down here. So m1 for aqueous solution, this is the m1 molarity, and this is mole per liter. Fine. Similarly we do the calculations for another two sets. Now coming to the organic part. So for organic part I have taken this will be changed to 2m1, and I have taken 10 ml of this is equal to 1 into m by 10 into V2. So here V2 is this, 10 ml I have taken, so I have written over here 10, and this much volume is consumed for of m by 10 sodium thiosulfate solution. So you just write down this V2 over there, and from there we are just going to calculate this m1 organic. Fine, this m1 stands for mole per liter. This is mole per liter. And in this manner we get m1 for organic and m1 for aqueous. So the KD, which is the distribution coefficient, is equal to concentration in one phase divided by concentration in another phase. So I have chosen organic divided by aqueous. And on dividing these two, this one, I'm just going to show you. I'm just going to divide this divided by this one. I get this value and this value. Taking average of these three, we are getting this. In some of the texts I have seen some 72 something is the partition coefficient for n-hexane and water system. But I repeat my experiment and I get again the same results. So I don't know where is the problem. You can check by yourself carefully, right? I hope you find this video helpful. If you find this video helpful, please like, share and subscribe. Thank you all. Thanks for watching.